This is the first of two videos corresponding to section 2.2 in Nicholson. That's on the topic of equations, matrices, and transformations. Remember, if the video goes too fast, you can always pause it, and you can also replay it and rewatch it as many times as you need. Last time we talked about how we would multiply a matrix by a vector. So if the matrix A is 2, negative 1, 3, 5, 0, 2, negative 3, 1, negative 3, 4, 1, 2, and the vector x is 2, 1, 0, negative 2, then we saw that we could multiply A times x by taking the first entry in x and multiplying it by the first column of A, and then adding to that the second entry in x by the second column in A, and adding to that the third entry in x by the third column in A, and the fourth entry in x to the fourth column in A. When we do this, we end up with the vector negative 7, 0, negative 6. And last time we didn't have a lot of ways of thinking about what this actually represented, so today's lesson we're going to start to dig into that a little bit deeper. Another problem that you might see related to this is if we're given vectors a1, a2, a3, and a4, and these are all column vectors in R3, meaning that they have 3 entries in them, and say that we're given that 5a1 plus 2a2 minus 3a3 plus a4 is equal to the matrix A times the column vector x, we want to find the vector x. So the way that we do this is using the same formula as we did above. We know that the matrix A is made up by those column vectors a1, a2, a3, and a4. So AX is the matrix a1, a2, a3, a4 times the column vector x1, x2, x3, x4. And when we multiply them together using the formula that we've been using, we see that x1 times a1 plus x2 times a2 plus x3 times a3 plus x4 times a4 is equal to the value that we were told, so 5a1 plus 2a2 minus 3a3 plus a4. And this allows us to just read off what the values of x must be. So x1 must be 5, x2 must be 2, x3 must be negative 3, and x4 must be 1. Alright, a new definition we have that the identity matrix is any square matrix, so n by n, with 1s on the main diagonal and 0s everywhere else. So for example, I sub 3 is the identity matrix that's a 3 by 3 matrix. So we have 1s going down the main diagonal and we have 0s everywhere else. It turns out that the identity matrix times any vector x is equal to the vector x. And we can prove this. I'm going to prove it just for a 3 by 3 matrix. So if I have I3 times the vector x1, x2, x3, that's going to be x1 times the first column of I, plus x2 times the second column of I, plus x3 times the third column of I. And when we work this out, we get the vector x1, x2, x3. So far we've seen that matrices can be used to represent systems of linear equations. We've also seen that they can represent linear combinations of vectors, as in this definition that we've been playing with. And today we're going to see one new way of looking at them. We're going to view them as functions that transform vectors. So let's suppose that we have the set of linear equations y1 equals x1 plus 2x2 and y2 equals 3x2. We know that we can write this as a matrix, and in fact we can set it up as an equation. So the matrix 1, 2, 0, 3 times the vector x1, x2 equals the vector y1, y2. I'm going to call the matrix F, the vector x1, x2 I'm going to call x, and the vector y1, y2 I'll call y. So, if x is the vector negative 2, 1, then f times x is negative 2 times the first column of f plus 1 times the second column of f, which comes out to 0, 3. And in this case, that's going to be the y value. So what I'd like you to do, I'm going to give you several vectors x, and I'd like you to pause the video and see if you can find the vectors y corresponding with each of these x vectors. So if x is 1, 1, if x is 1, negative 1, if x is negative 1, 1, and finally if x is negative 1, 1. Okay, so hopefully you paused the video and you were able to find the vectors y corresponding with each of these vectors x. You should have gotten that y corresponding to 1, 1 would be the vector 3, 3. Y corresponding to the vector 1, negative 1 should be negative 1, negative 3. Y corresponding to the vector negative 1, negative 1 should be negative 3, negative 3. And y corresponding to the vector negative 1, 1 is 1, 3. So in each case, we just took the matrix F and we multiplied it by the vector x. So I'm going to give names to each of these. You can see that I named the first vector x. I'm going to name that A. And the second vector x I'll call B, and then C, and then D. And then I can call each of these new y vectors A prime, B prime, C prime, and D prime. So when we look at the graphs of these vectors, I'm going to look at them as points. So in other words, the point A is going to be at the point, or at the coordinates 1, 1. B is going to be at the coordinates 1, negative 1. C is going to be at negative 1, negative 1. And D is going to be at negative 1, 1. And I can connect each of these points with a straight line. So notice that we get this cute little square with center at the origin. Now I'm going to graph the points A prime, B prime, C prime, and D prime. So on the same set of axes, A prime we saw was at the point 3, 3. B prime is at the point negative 1, negative 3. C prime is at negative 3, negative 3. And D prime is at 1, 3. And so again, I'm going to connect each of these with a line. And you'll notice that what we've done is we've transformed the points. So A got mapped to A prime, B got mapped to B prime, C got mapped to C prime, and D got mapped to D prime, where the mapping happened by multiplying the vector by x, or by f. You'll also notice that the origin itself gets mapped to the origin. So in other words, f times the 0 vector is the 0 vector. And so we can treat f as a function. It maps points in R2 to different points in R2. So once again, we're looking at f as a function taking vectors in R2 to other vectors in R2. And so we're going to call this function t sub f. And you might have seen this notation for functions before. Usually when we write t sub f and then a colon and then R2, arrow R2, what we mean is that the domain of the function is R2. So that's that first space. And the codomain, which sometimes you've called the range in the past, we're going to call it the codomain. The codomain is also R2 in this case, but that'll be the second space that you see. So TF is going to be called a transformation. And we can look at other examples of transformations. So here I have a matrix 1, 0, 2, negative 1, 3, 4. The function corresponding to that transformation is t sub a, and that's going to go from R2 to R3. So if I let x be the vector 1, negative 1, then ta of x is going to be the same thing as just a times the vector x. And we know how to work this out now. We're going to do 1 times the first column plus negative 1 times the second column and we'll end up with 1, 3, negative 1. So that's the output, that's the y vector. Notice that the vector that we started with was a two-dimensional vector, so that lived in R2, and the vector that we ended with is a three-dimensional vector, so that's in R3. And so we can view this as something that takes the vector x in R2 to the vector y in R3, and we're calling this function t sub a. Just to give us more vocabulary, we call y the image of x under the function t sub a. We call it the image because it is the thing that's being looked at when we plug in x. Notice that when A is a 3 by 2 matrix, the function, or the transformation t sub a, goes from R2 to R3. So in other words, when we talk about rows and columns, remember 3 is the number of rows in the matrix and 2 is the number of columns. T sub a is going to go from a two-dimensional space to a three-dimensional space. In general, if A is an m by n matrix, then T sub a goes from an n-dimensional space to an m-dimensional space. In the next video, we're going to see more about how these transformations behave.